Alright, now we are in step 4, or part 4 rather, where we're looking at conjugate bases and conjugate acids. And so what we have to understand is, you can begin with the parent, or you could begin with the conjugate. And so we have to, make sure that, first off, in order to be, a conjugate, acid or base, you must be in an equilibrium process with the parent. Meaning that, just to relay that in terms of an acid example, if we look at our general acid plus H2O in a one-way reaction, we would produce, hydronium ion and our A minus. Now we can call this a conjugate but it's not a conjugate base. And that's basically because of our arrow, right? This is not equilibrium. However, if we have, kind of a general acid, such as, again, we'll just be still general, so we'll still call it HA. Right, we're still producing, the same general types of products. But now we have a conjugate base. And that's because we have an equilibrium process. So that's, what we have to realize is that there are conjugates, and then there are conjugate bases, such as we have with our A minus in a general sense. We can say, this is, for acids. For bases, we would have, really with our strong base, it's really more this metal, hydroxide. And it's somewhat redundant in the fact that the hydroxide pulls off a proton from H2O, and that, makes H2O. So oftentimes we don't write the water with the strong bases. But here we could say that the metal is a conjugate. Right? We're producing hydronium for acids. We're producing hydroxide for bases. So the other component that's not, affecting the pH would be the metal that's positive. However, this is not a conjugate acid because we don't have, or there isn't an equilibrium process. So we're not going to see conjugates of metal hydroxides, just like we're not going to see, as far as a conjugate acid, just like we're not going to see conjugate bases of a strong acid like hydrochloric acid. But then if we go to the weaker side of the picture, we can show our base with the lone pair, often the nitrogen atom, producing again a cation, just like we see with the metal cation above, as well as hydroxide. But this is now a conjugate acid. And that's because of our equilibrium process. So if we just scroll back just a little bit, we can see the difference here. Again, something I've been trying to highlight in the last lecture, where we have a strong acid or we have a weak acid. Right, and the difference is whether you have a one-way reaction or an equilibrium process. And we see the same thing occurs here, where we have a strong base, and again, no equilibrium process, really just dissociation in the dissolution process, and then we have a weak base. And now we have the equilibrium. So just trying to recognize, the relationship, again, between the parent and the conjugate, and where we're going is really specifically to the nature of conjugate acids and conjugate bases. Conjugates tend to be charged. We tend to see a positive for conjugate acids. And we see a negative charge for the conjugate bases. So they often start as salts. And this means that, you can't weigh out a cation or anion. Right? They need another charge. They need, an opposite charge, or they need a counter ion. So these conjugates come in forms of salts. And so, for instance, if we were to look at, let's say, acetic acid, I'm not drawing all the materials. I'm just trying to show the relationship between acetic acid and then its conjugate acetate, right? So here we have our weak parent acid, and on the right we then have the weak conjugate base. So to start with acetate, this conjugate base, I need to have a salt of acetate. And that's simply meaning I want to pair it with a metal that is positively charged. So, for instance, we could have sodium acetate. Or, potassium acetate. Right, where we have, in terms of charge, our sodium is +1, so is our potassium. And so that means our acetate has that -1 charge on it. These would be solids. And when we put them into water, right, we see the dissociation occur, and in both cases we get acetate plus then, some metal. The metal here is a spectator. It's just a counter ion. No chemistry. And then we have here our conjugate base. And then we would go further with that. So that's how these conjugates come at us. They actually come in the form of salts. Alternatively, we could be starting with a parent base. Right, looking at the base side of things, here is our parent weak base, and then on the other side we have now the conjugate acid, which is also weak. That's why we have the equilibrium process. So, if I want to start with the methyl ammonium, namely the CH3NH3 that's positively charged, right? And remember, that's our conjugate acid. Right, I need to start with its salt, which carries the counter ion as a halide. So looking at chloride, bromide, iodide, those are the ones that we tend to see. So if I start with methyl ammonium chloride or methyl ammonium iodide, right, these would be solid salts that I would begin with, where I have a -1 for the halide and then a +1 for the ammonium. So putting that, into water, that reveals the ammonium ion. And then we also have our halide. So just like before, our halide here is a spectator. Right? There's no chemistry going on with it, but on the other side of things, we have now a conjugate acid that can then affect the actual, the actual pH. So let's look at, some of the methodologies, and there's really only one, for conjugate calculations. And if we start with, acids or, conjugate bases, of weak acids. So what we find with conjugate bases of weak acids and conjugates in general is you will only find the Ka for a parent acid. Never a Kb for its conjugate base. And so that's one thing that we have to understand, is there's that aspect of it. Also, we want to write the acid-base equilibrium reaction in terms of what we have initial. So in this case, we would have conjugate base initial. And there would be no parent acid initial. So we want to, do a couple things. We want to make sure that we write the equilibrium reactions in terms of what we have initial. In this case, conjugate base initial. So if we look at, for instance, a general acid where we have, RCO2H. So the R group here stands for anything. So any type of side chain or whatever. But what we have here is a parent weak acid, right? And that's going to generate a conjugate base and hydronium ion. And we have a Ka associated with that. So this is the, equilibrium reaction if starting with, a parent acid. This is our equilibrium. But now that we're in the conjugate side of things, I could start with the conjugate, namely the RCO2 minus. In this case, this is a KB. And we form the parent acid, but now we also form hydroxide. So if starting, with a conjugate base, this is our equilibrium. And notice that we have the connection between, Ka and hydronium ion, as well as the connection between hydroxide and Kb. And so there is a relationship between the Ka of a parent acid and the Kb of its conjugate. And our relationship is that Ka basically times our Kb is equal to Kw. And this is what I call the Ka-Kb shuffle. Again, since conjugates don't have a constant that we can look up, we need to do this Ka-Kb shuffle. So that's why we have to do the shuffle, is because, there are no tables to actually look up the conjugates. All they post are the parents. So we have to look up the parent, but then put it into perspective of the conjugate. And that's ultimately very confusing for students, right? As well as, just realizing that now the reaction is actually written completely the opposite to what we were talking about in the last lecture with starting with parents. Starting with conjugates now just throws everything on the flip side of that. For now the second piece, which would be now conjugate, acids of parent bases. Again, you will not find, or rather you will, only find the Kb for the parent, never the Ka for the conjugate acid. So we still have the same thing kind of running as we did above in terms of that. So you want to write, the equilibrium reaction with what you have initial. So here we have, initial conjugate acid. Right, there's no initial parent base. So that means that we would write it in terms of, we were to think about our parent base. Again, we have our R group here, which could be anything. And here we have a KB defining that process. And so this would be, if starting with our parent base, this is the equilibrium. But we now could also start with our conjugate acid. Where here now we have a KB. Oh, I'm sorry, we have a Ka. Again, Ka, because we're making hydronium ion. Kb, because we're producing hydroxide. So this would be our equilibrium if starting with conjugate acid. So that's the equilibrium process for it. But again, we will never be able to find that Ka. So, again, only Kb for the parent can be found in tables. And the Ka, Kb shuffle is required. To get in terms of the conjugate acid, namely our Ka. So we have to do the same type of shuffle with this expression. Lastly, if assumptions are made, and assumption check is required. So that's the methodology behind the process. It's really going to be exactly the same as what we've been doing in the past, but we just need to add, really just add another step. Meaning that if we look at our, method for weak conjugate acids or bases, we have really a general method. One, identify the starting material. Two would then be what is the equilibrium reaction or reaction in general. I guess we could say there's two parts of that, because once we have our equilibrium reaction, then we can write our K. And sometimes here we might need the Ka, Kb shuffle. We then go to our ice table. And lastly, we would then substitute into K. Right here, this would be, Ka or Kb. And we want to solve. And again, here's another area where we, might need that Ka, Kb shuffle. Just depends on what the question is asking, if they're giving it something to us in the beginning or if we're solving for something at the end. So the method is the same, it's just now that we really have a lot more in terms of the starting materials, right? We could identify this as strong acid or base. We could identify this as weak acid or base. And now we have a third possibility, which is a weak conjugate acid or base. And it's this weak conjugate acid base piece that results in the need to do the Ka, Kb shuffle. So we've already covered examples of the top two with strong and weak parents. Here, maybe we can classify that a little bit more. Right now we're going to get into conjugates. So let's look at an example of a conjugate base. So we want to calculate the pH of a solution in which 4.2 grams of sodium benzoate has the formula C6H5CO2Na. So we have that 4.2 grams of sodium benzoate dissolved in 500 milliliters of aqueous solution. The Ka for benzoic acid, is C6H5CO2H, is 5.8 times 10 to the negative fifth. So there's our question. Trying to calculate the pH of a solution, right? We have some initial materials here, and so the first step in our method is identify. And with this identification process, really it's this structure that we see of our CO2, metal, right, where our metal is going to be positive, and then we have this negative feature. And that's what we see with the C6H5CO2Na, right? We see our CO2 minus, and we see our Na plus. And so these are telling us we have a conjugate base as a result. Right? We're not beginning with any of the benzoic acid. Our initial conditions are here. We have 4.2 grams of the sodium benzoate in 500 milliliters of aqueous solution. And so here is our salt. And in this case, it's a conjugate base, with the salt being the minus and the plus. The sodium doesn't do anything, it's a spectator, but the C6H5CO2 minus is then the conjugate base portion of the molecule. So that takes us to our reaction. And so we're just looking at the conjugate reacting with water to produce the parent and hydroxide. And we have a Kb that's defining that process. And our Kb would be equal to our products, the C6H5CO2H benzoic acid, times our hydroxide over our conjugate. Again, I've dropped out the sodium because remember the sodium is a spectator and does not display any chemistry for us in terms of this acid-base chemistry. So at this particular spot, right, we don't have a Kb, we have a Ka equal to 5.8 times 10 to the negative fifth, and that Ka is for the parent. So that's why we need to do the Ka-Kb shuffle as a result. So our Kb is going to be equal to our Kw divided by our Ka. So we have 1 times 10 to the negative 14th for our Kw. We had 5.8 times 10 to the negative fifth for our Ka. And so we end up with a Kb that is equal to 1.72 times 10 to the negative 10th. And that Kb is equal to that ratio that we have above. So there's that kind of new step now that's being thrown into the method is, once we recognize that it's a conjugate, now we have to do the Ka, Kb shuffle. Right, and that's because of that idea that it is a conjugate base. So that takes us to the third step. Now we're under familiar ground with our our ice table. We have our starting material, the benzoate. And then we have our products, the benzoic acid and our hydroxide. And so we have our initial, our change, and our equilibrium like we've done in the past. So now we need to fill in some information. You've got to go back and remember we have that mass and volume in the question. I underlined prior. Right, we have 4.2 grams of sodium benzoate in 500 milliliters of aqueous solution. So we need to get that into a mole value, or really a molar value. As far as our initial set of conditions. So we would start with our 4.2 grams. Of the sodium benzoate. We would divide by its molar mass of 144 grams per mole. And so that's getting us into moles of the sodium benzoate. Terms of moles of our benzoate, since there's, it's really a one-to-one process, so a little bit redundant, but right, because it's a one-to-one dissociation, but that's showing us getting out of moles of one material and getting in moles of another. And then we can divide by our volume that we had, which was the 500 milliliters or 0.5 liters, to get a value of 0.0583 molar in terms of our benzoate initial. So that's what we're plugging in above. There's no mention of the products, so those would both be 0. And again, there's our direction of change. Minus change for our starting materials. Positive change for our products, and these are all 1 to 1 to 1. And so we have 0.0583 minus x. And then we got x and x for our equilibrium values. So now that we have all of that, we can basically substitute and solve. And basically we're solving for x, which is taking us to hydroxide ion concentration, but then we can get to POH and then pH as a result. So our Kb, just to refresh our memories, was the parent acid product times hydroxide over the conjugate base. We have that Kb of 1.72 times 10 to the negative 10th is then equal to essentially x squared in the numerator over 0.0583 minus x. So here we can, if we like, we can use the quadratic or assume, x is small relative to an initial concentration, which we can do here. Our K B is less than 1 times 10 to the negative 4th, and we have starting material initial, so we can assume so that x in the denominator is going to go to 0, and that makes life a little bit easier in solving for our x value. So we would get something that looks like this, right? Our x squared would be equal to the 1.72 times 10 to the negative 10th times our 0.0583. And we would want to take the square root of both sides. And x, which equals hydroxide, remember, is 3.167 times 10 to the negative 6th molar. So there's our angle to get at POH, where we just need to take the negative log now of the 3.167 times 10 to the negative 6, and we get a POH equal to 5.49. And then our pH would be equal to 14 minus the POH, or 14 minus my 5.49, give me a pH of 8.51. So that's how we got to our pH, is first solving for x after we did the Ka, Kb shuffle and made an assumption. Then getting our hydroxide ion concentration, we can get POH, and then convert that to pH. We need to do an assumption check. So I'm going to look at percent change, which would be equal to x over our initial concentration of our conjugate base, the benzoate. So our change here was the 3.167 times 10 to the negative 6 molar. Our initial was 0.0583 molar times 100. And we get a value of 0.005% change, and that means we have a good assumption. So 8.51 is our answer. So that's an example of a conjugate base. Let's do another example. Let's do an example of a conjugate acid. So a solution of morphine hydrochloride And morphine hydrochloride has the formula of C17H19O3 and HCl. So we have a solution of morphine hydrochloride prepared by dissolving 0.05 moles of the morphine hydrochloride salt in 500 milliliters of aqueous solution. If the pH is equal to 4.6, calculate the pKb for morphine. And morphine has the formula C17H19O3 nitrogen, N with a lone pair. So that is our question. We have a solution of morphine hydrochloride salt. We see the formula there. Here's our initial set of conditions. We have 0.05 moles of the salt in 500 milliliters of solution. So that's getting us to an initial concentration of our salt, of our conjugate acid that we're seeing here. And we also have a pH equal to 4.6, which is telling us our hydronium ion at equilibrium. And we want to use all that to figure out the pKb. So let's start first with our identification. And so we need to do this by structure here. We can't simply look at Ka or Kb because now we have conjugates in the picture. And so for our structure, we see that we have this RNHX, where our nitrogen is positive and our X is negative. And that's just apparent in the formula. Right, that's basically our R group is that tail, and then we have the NHCl. So our chloride is our X, and then there is our ammonium. The chloride here is a spectator. So remember, there's no chemistry. These acid-base chemistry that we see. And so that means that we have a weak conjugate acid as a result. So that's what we have there initially. And so that's what we need to write our reaction in terms of. So we're going to start with the ammonium form of morphine, where we have that NH plus. That's going to be plus our water to produce then the parent base, morphine, plus then H3O plus. So there is our reaction that we're looking at. And that reaction is defined by a Ka. And so that Ka is going to be equal to our products over our starting material. So we have the morphine, we have hydronium ion as our products, and then we have the ammonium form of the morphine as our starting material. So we don't know the Ka or Kb, right? We're really asking to solve for the K, really the pKb, but we're going to first have to get at our Ka and solve that, and then we can do the shuffle. So while we did the Ka-Kb shuffle in step 2 of the last example, we're going to find that shuffle is going to happen a little bit later in this case, because we have everything to fill out the ice table completely. So with our ice table, we're putting in all of our important components. So we have our starting material, we have our products, and we should have enough information above to get at our initial, our change, and our equilibrium. So going back, we realized that we could figure out the initial conditions here, where we have 0.05 moles of our NH plus, just using some shorthand there, divided by our 0.5 liters of solution, we get 0.1 molar, and that's looking at our ammonium form of the morphine, where we have our NH plus, and so this is initial that we're seeing here. So that's what's getting plugged in for its initial condition. And then there's no mention of the other components, so those would both be 0. See this direction of change a lot with acid-base chemistry, where we're seeing decrease in starting materials, increase in products, and they're all 1 to 1 to 1. And so we also know pH here, so we do know what the change is going to be. We can figure out our hydronium ion at equilibrium by taking 10 to the minus pH, or 10 to the minus 4.6, which gives us a value of 2.51 times 10 to the negative 5th molar. So that is basically our change that we're seeing now. So at equilibrium, we have for our hydronium 2.51 times 10 to the negative 5th, right? And that's also now telling us what X is, since we begin with 0 of it. So we would have a plus 2.51 times 10 to the negative 5th, right? We'd see the same thing for our parent product. And then we would have 0.1 minus that, but we would have the minus the 2.51 times 10 to the negative third, or I'm sorry, 10 to the negative 5th. Not much of a change in that number. So we would end up with 2.51 times 10 to the negative 5th, again for our parent base product, and then 0.1 minus 2.51 times 10 to the negative fifth for our ammonium form of the morphine. So now we can substitute into Ka and solve for Ka. Right, then we need to do the Ka Kb shuffle, and that's going to get us into Kb, and then we can get to pKb. So again, this is all in terms of the conjugate, right? So that's what we're solving for here, right, is our Ka for the conjugate acid. But ultimately what we want is the Kb or pKb at the very end of the parent base. So first we have to solve for our Ka, then we can solve for the answer, the Kb and pKb. So our Ka would be equal, again, just to remind us of our products, right, over our starting materials. We're trying to solve for our Ka, so we're going up to the top there and plugging in our values. We have values for all of the equilibrium constituents. So we have our products, which have the same concentration of 2.51 times 10 to the negative fifth. And then our starting material, which will be 0.1 minus 2.51 times 10 to the negative fifth. And we end up with a Ka equal to 6.3 times 10 to the negative ninth. So here is where we need the Ka-Kb shuffle. So our Kb here is our Kw over our Ka. So 1 times 10 to the negative 14th divided by our 6.3 times 10 to the negative ninth. And we get a value of 1.59 times 10 to the negative 6 for our Kb, which is allowing us now to access our pKb. And so the pKb here would be equal to 5.80. No assumptions were made in this calculation, so no need to make an assumption check. So there's an example of a conjugate acid. So we did a conjugate base example where we had to figure out pH. We did a conjugate base example, a conjugate acid example here where we actually had to figure out Kb. So looking at both sides of the equal sign in terms of examples to help with your practice. But that is all we have now for our conjugates.